Welcome to the fifth lecture on this series on PH 4105 Advanced Mathematical Physics. Here we are discussing differential geometry at the moment, and in our previous lectures we had already set up the basic stage in which differential geometry is played. This is the idea of differentiable manifolds. Let me remind you that a set M is called a manifold if it is equipped with something called a CK atlas. And here K is an integer. If K is 1 or more, then what we have is called a differentiable manifold. And if K is 0, what we have is a topological manifold. Now, what specifying the CK atlas on a set M does is that it gives us a way in which we can do calculus on M. That is, it equips M with a differential structure. The major players on this, at least the beginning point, is that we assign coordinates to points on a set M by using charts. These coordinates are a bunch of real numbers. They may also be complex numbers if we are talking of complex manifolds, but in this course we focus on real manifolds. Now, basically what this allows us to do is convert problems involving structures on the set M, like functions defined on this, or more complicated structures that we are going to meet later, essentially into things which depend on a bunch of real numbers. So whatever we have learned about calculus of more than one real number can actually be brought to bear on this theory here. Now, we have already discussed this in the past in some detail, but let me quickly remind you what a chart is. As I've said, a chart assigns coordinates, let's say x1, x2 up to xn, to every point P in a subset U of M. This U is the domain of the chart, and the chart comes equipped with a function phi which assigns to every point P these numbers x1p, x2p, x3p, xnp. Of course, this assignment is done only to points P within U, so it may or may not cover the entire set. In order to cover the entire set, you may very well need multiple charts, and that is where the issue of compatibility comes in. So if you have two charts on the manifold M, let's call them U phi and V chi. U and V are the respective domains, and phi and chi are the actual maps. These two charts are called CK compatible or CK related if either their domains are disjoint, or if both phi of U intersection V and chi acting on U intersection V are open subsets of Rn, and the transition functions which allow you to translate coordinates assigned by chi to coordinates assigned by phi composite chi inverse, or the other way around, chi composite phi inverse, which allows you to relate the coordinates assigned by phi to those assigned by chi. These happen to be functions of real variables, in that effectively n real functions of n real variables, and these are CK functions. That is, they have derivatives up to the kth order, and the partial kth order derivatives are also continuous. Now, two charts may or may not cover the entire set M, but if you have a collection of charts U1, phi1, U2, phi2, etc., such that their domains cover all of M, and if each pair of charts here are CK compatible, then we call the resulting structure a CK subatlas. And it is this CK subatlas which allows you to do calculus on all of M. And the actual differential structure that a given CK subatlas implies is that you take all possible charts that are CK compatible with every chart in a CK subatlas, and you end up with a CK atlas. Now, this was a very quick recap of whatever we have done before, and as I've said, it is the CK atlas which ultimately gives you the structure that you need to do calculus on a set M. Effectively, by making the set M look, at least locally, like an open subset of Rn, where we can use the standard tools of multivariable calculus. Of course, when we say that a differential structure allows you to do calculus on M, the first thing that we mean is that it allows us to talk about whether a function f defined on a manifold M is differentiable or not. For this, let us begin with a simple case where we are talking of a function f which takes M to the set of real numbers. Now, when do we say that this is differentiable at a point P belonging to the domain U of a chart? For this, what we need to do is to realize that we do not have a direct way of doing calculus on an arbitrary set, but we can do calculus on functions of multiple number of real variables. And what the chart U, phi allows you to do is that it allows you to define something which I have called a proxy function in a previous video, f composite phi inverse, and note that f of p is exactly equal to f composite phi inverse acting on phi of p. Phi of p are the bunch of real numbers which provide coordinates for the point P. So what you have here is the value of the function at a point P of the manifold is actually the value of the proxy function acting on the coordinates of the point that we are talking about. And when do we say the function f is differentiable at the point P? We actually look at the proxy function f composite phi inverse. If that is differentiable at the point phi of P using the standard notion of multivariable calculus, then we say the function f is differentiable. In fact, if f composite phi inverse is a CR function, that is, it has derivatives up to order R, which are also continuous, then you say the function f defined on the manifold is also a CR function. Of course, since you may have multiple charts covering your set M, and point P may actually belong to the domain of multiple charts, the question of compatibility of these charts come into play here. In order that this conclusion that f is a CR function be independent of which particular chart we choose, we must have the condition that R is less than or equal to K. So on a CK manifold, which is equate with charts whose domains cover the entire set, and where the charts are pairwise CK compatible, can only talk of differentiability up to order K. Talking about differentiability of an order more than K does not really make sense, because conclusions about that will be valid, if at all, only in certain charts and may be violated in other charts. On the other hand, as long as R is less than or equal to K, then the conclusion that a function f is of class CR, that is, it is differentiable of class CR, is independent of which particular chart you are using. Now, this notion of proxy functions will recur over and over again in succeeding lectures. And this issue may seem a bit unnatural to some of you. So before we go on to the more complicated concept of doing calculus on functions from one non-trivial differentiable manifold to another, let me stick to this issue of proxy functions and try to discuss them a bit further. As we have already said, the reason why we can use proxy functions at all is that the function f composite phi inverse, when acting on a bunch of numbers x1p, x2p up to xnp, which make up phi of p, returns exactly the same value as does the function f when it acts directly on the point P of the manifold. However, we have no notion about how to do calculus directly with the function f, but f composite phi inverse being a function whose domain is phi of u, an open subset of Rn, and whose image is of course R, is something we can do calculus with. So, in a sense, this is just a matter of necessity. We can't do calculus with f, but we can do calculus with f composite phi inverse. However, it might still seem a bit unnatural to you that we are using a different function altogether when we are talking about the properties of f. But if you think about it, it's really not that unnatural. And to understand that, let us take a look at an example. The example that I'm going to talk about now is one in which we consider our manifold M to be S2, or to be more concrete, the surface of the Earth, which is approximately at least the same as the surface of a sphere. Now, the temperature at different points on the Earth at a given instant of time may very well be a function defined on the manifold. Now, the way in which you should actually specify this function on the manifold is to specify the temperature at each and every point on the Earth. Well, each and every point may be too much to do, but at least we could do something like stating that the temperature at GPO in Calcutta is 21 degrees Celsius right now. Say the temperature at Alipurduar, the station, is 16 degrees Celsius. The temperature at Leh Airport is, say, 4 degrees Celsius. That at the Sydney Opera House is 24 degrees Celsius, and so on and so forth. Of course, this specification of the temperature at every point on the surface of the Earth is way too unwieldy to actually do something with. So what we usually talk about is an approximation to this, which is an analytic function, which could be some approximation to the actual function. Now, this function is almost invariably specified in terms of a two-variable function, t of alpha comma beta, where alpha typically is the latitude of the point and a beta is the longitude. If you have forgotten those concepts from school level geography, you can see latitude and longitude drawn in the picture. Of course, in physics we often use the colatitude, which is the angle measured from the z-axis, or the line joining the center of the Earth to the North Pole, and not really the latitude. But the idea is basically the same, no matter whether we use the latitude or the colatitude. The important point to note here is that the pair of numbers alpha and beta, the latitude and longitude of a point, are really coordinates of the point which are being obtained using a specific chart. So the function that we would usually use to describe a function on the surface of the Earth is actually a proxy function, not a function where the input is a precise point on the Earth. Rather, the input is a pair of numbers which stand in for a particular point. And this theme recurs over and over again. When we talk about a function on any manifold, we usually talk about the value that the function takes given a bunch of arguments, which are typically numbers which tell you which point on the manifold we are talking about. But these numbers are really the coordinates of the point, not the point itself. And so what we are really using, almost invariably, is the proxy function, which acts on these coordinates. So while we have been careful to distinguish the function f from the proxy function f composite phi inverse, very often in practical usage, the distinction is rather blurred. When we talk about a function on a manifold, we usually, more often than not, are actually talking about the proxy function. Now with this out of the way, let us now move on to discuss a slightly more involved case, that of a map between two different differentiable manifolds, capital M and capital N. In this picture, I have tried to denote such a map by this blue arrow here. The map F takes a point P belonging to the manifold M to its image f of p, which belongs, of course, to another manifold capital N. Now, we want to talk about differentiability of this particular map small f. And once again, we are faced with the problem that we cannot really do calculus on an arbitrary manifold. But we can definitely do calculus on open subsets of Rm and Rn. Notice, here I have assumed that my manifold capital M is a small m dimensional manifold. So it has charts, in particular it has a chart capital U which contains the point P, which we are interested in right now. U, of course, is the domain of the chart and the map is phi. So point P acquires coordinates given by phi of P. We can call these coordinates x1, x2, xn. These numbers as the coordinates of the point P. On the other hand, f of P, the image of P under the map F, also can be given coordinates, this time using a chart v, chi, where v is a subset of capital N, to which f of P belongs, and the map chi maps f of P to the point chi f of P of Rn. Remember, we are assuming that capital N here is an n-dimensional manifold. So, chi f of P, of course, is a bunch of n real numbers. Let's call them y1, y2, yn. Notice that chi of f of P, which are the coordinates which we assign the image of the function f, is essentially a bunch of n real numbers, whereas the point P can be denoted here by a bunch of m real numbers, the components of phi of P, what I have called x1, x2, xn. And how are these related to each other? Chi of f of P is certainly given by this function, chi composite f composite phi inverse, acting on phi of P. And what does this function really do? It takes the m coordinates x1, x2 up to xm, the m real numbers which denote the point P. These are, of course, the components of phi P. When this function is applied on these m coordinates, the resulting n numbers are nothing but the coordinates of f of P under the chart v, chi. So now what we have done is we have translated this function, which was between two manifolds, into a new function, our proxy function in this case, which acts between an open subset phi of u of Rm and another open subset phi of v of Rn. And here we can carry out standard calculus. This allows us to define differentiability of a function between two manifolds M and N in the following manner. Given two manifolds M and N, a function f from M to N is going to be called differentiable of class CR at a point P belonging to M if given charts u, phi on M and v, chi on N. You must realize that all I'm doing here is formally stating whatever the picture above had told us, with P belonging to U and f of P belonging to V. Remember, if you have a differentiable structure on M and N, which is what after all makes them differentiable manifolds, you have charts which cover the entire manifold. So there will definitely be some chart U, or rather some chart with domain U to which P belongs. And similarly, f of P, an element of capital N, must belong to some chart v, chi. Now, in this case, the proxy function that we use is chi composite f composite phi inverse, which is a map between m real numbers to n real numbers. And if this function is differentiable of class CR at phi of P, we are going to call the function f differentiable of class CR. Once again, in order that this statement makes sense, even if we change the chart or charts that we are using, we must keep to a value of R which is smaller than or at best equal to K. To see this, let us consider the situation where we have changed our charts. Instead of using u, phi, we are using u prime, phi prime on n, and we have replaced v, chi on n by a new chart v prime, chi prime. Of course, p has to belong to u prime as well for this to work at all. So, p is a member of u intersection u prime. And similarly, f of p has to be in v intersection v prime. Now, once these new charts are being used, the new proxy function is chi prime composite f composite phi prime inverse. But that's nothing but chi prime composite chi inverse composed with our original proxy function chi composite f composite phi inverse composed further with phi composite phi prime inverse. Notice phi composite phi prime inverse is nothing but the transition function between the charts u prime phi prime and u, phi on M, and because M is a CK manifold, then phi composite phi prime inverse must be differentiable of class CK. Similarly, chi prime composite chi prime inverse being the transition function between the charts v, chi and v prime, chi prime on N must also be a CK function. So this is the composition of functions, each of which are at least R times differentiable. Remember, R is less than or equal to K. Therefore, the resulting proxy function, the function that we get when we are using different charts, is also differentiable of class CR. So our notion of differentiability of the function f, which remember is nothing other than the differentiability class of the proxy function, stays unchanged under this change of charts. You may have realized that we have actually taken both M and N to be CK manifolds. It is of course possible that M and N are manifolds of different degrees of smoothness. M may be a K order manifold and N may be a K prime order manifold. In such a case, for our conclusion about f being differentiable of class CR to hold, irrespective of what chart we are using, R must be smaller than or equal to the minimum of the two smoothness degrees K and K prime. Note that in the definition above, we have talked about differentiability of the function f at a point P. Of course, the extension to a function f from M to N being called differentiable of class CR is simple. A function f from M to N is called differentiable of class CR if it is differentiable of class CR at all points P belonging to M. Now for some nomenclature. The collection of all CR functions f from M to R, the special case where the image is a set of real numbers, is denoted by CRM, and the collection of all CR functions f from M to N is similarly denoted by CR M, N. Now, among all of these collections of differentiable functions, CRM is somewhat special. That's basically because of the fact that here all the functions map onto the real line, which means it's very easy to add the results which the functions produce and to multiply them. And so, for functions in CRM, you can easily define addition of functions and multiplication of functions. Please note that despite the fact that this seems to be an obvious statement to make, this is really a definition of how two functions f and g can be added. F plus g evaluated at a point P is defined to be the sum of the results f of p and g of p. Because f of p and g of p are both real numbers, adding them together is a perfectly sensible thing to do. And by the same token, here what we have done is defined the product of two functions f and g. Fg is a function which, when evaluated at the point p, gives us f of p times g of p. Once again, here we are actually just multiplying two real numbers, the values that f and g take at the point p. And so this is a perfectly sensible thing to do. What is very important is that once we define addition and multiplication of m to r functions in this manner, the collection CRM now has a rather nice algebraic structure. And this algebraic structure is what mathematicians call a ring. A ring basically is such a set where you have two operations, plus and multiplication, and these two operations speak nicely to each other, by which I mean results like this hold. F times g plus h distributes nicely into fg plus fh, and so on. So basically a ring is a set in which you can add and multiply, and the multiplication talks nicely to the addition. Indeed, another algebraic system which shares many of these properties is a very familiar one, the set of all real numbers under addition or multiplication. And the set of all complex numbers, for example, also has such properties. But what makes R and C different is that they are actually one step beyond rings. They are what are called fields. This is, of course, the mathematician's field and not what a physicist means by a field. A field is, roughly speaking, a set where you can add, multiply, and divide by non-zero entries. Zero here means basically the identity element of what we are calling addition. Now, the reason why CRM is just a ring and not a field is as follows. If you were to try to divide two functions, the natural definition to use, and one that would automatically follow from the definition of multiplication here, is that f over g should be a function which, when evaluated at a point p, should be f of p by g of p. Now, this is a legitimate operation as long as g of p is 0 nowhere. But if a function takes the value 0 at one or more points on the manifold, then f by g will not be a well-defined entity. At the point p on M where g of p vanishes, f by g simply cannot be defined there, and so f by g is not going to be a function over the manifold M. In other words, you are not allowed to divide by functions which vanish at one or more points on the manifold. But on a field, you should be able to divide by every non-zero element. Every element which is not the additive identity. In the set of all functions, the additive identity is simply the zero function, the function which returns 0 everywhere, so that adding it to any function f does not change its value at any point. Of course, you cannot divide by the zero function, but as we have seen, you cannot divide by functions which vanish at even just one point on the manifold, let alone all points. So there are non-zero elements in this set which you cannot divide by, and that is why CRM is not a field, it is just a ring where addition and multiplication is well defined. Division by all non-zero elements is not necessarily well defined. This ring structure of CRM is going to be very important in many of the discussions that we are going to have in the future. From this point on, unless otherwise mentioned, all our manifolds will be smooth manifolds. So all our charts will be essentially C infinity compatible with each other. So this restriction of R, the differentiability class of a function, having to be less than or equal to the degree of smoothness of our manifold is no longer a concern to be worried about, simply because if K is infinite, all R's are covered. If a function is differentiable of any order according to one chart, it is differentiable of the same order according to any other chart in a C infinity manifold. And we are not really going to worry about functions which are differentiable only a finite number of times. Unless otherwise mentioned, we are going to consider all our functions to be C infinity functions. Functions which are differentiable an arbitrary number of times. Now, given two smooth manifolds M and N, two structures which are very important as we have seen are C infinity M and C infinity N, the set of all real valued smooth functions on M and N respectively. Now, given a function, a smooth function, between the two manifolds M and N, there is a rather nice way to relate a smooth function on N to another on M. Or what we can say is we can pull back a smooth function on the image space N and use it to produce a smooth function on the domain M. So as I have just already used the word, this operation is called the pullback. And the way we formally define it is as follows. Given a map psi, a smooth map between M and N, that is an element of C infinity M, N, and a function f, some arbitrary smooth function on N, a member of C infinity N, we define a pullback by psi of f, which is denoted by this entity psi with a star upstairs acting on f. And this thing is defined through this relationship. Psi star f is simply defined to be the composition of f and psi. This is f after psi. So this is a map which takes you from M to R and is shown pictorially here. Here you have the manifold M, which is our domain of the map psi, and the map psi takes you from M to N, and in particular takes the point P to the point psi P. Now f is a function defined on N, so it takes every point on N to the real line, and here in particular it takes psi of P to a given point on the real line. So what does the pullback function do? It actually applies f after applying psi. So the pulled back function is a function on M, and acting on a point P of M, what it does is first applies psi to get psi of P, then it applies f to give you a point on the real line. So this is what psi star f is. What is very important is that this operation composes together two smooth functions, f, which is a smooth function from N to R, and psi, a smooth function between M and N. And as a result, the resulting function psi star f is actually a smooth function on M. So it's a member of C infinity M. So you can think of psi star essentially as a map which takes elements from C infinity N and pulls them back to C infinity M. In particular, it takes a function f and pulls it back to this psi star f function, which as we have just defined is f composite psi. While this sounds perfectly reasonable, we need a formal proof of this fact. Now to check whether psi star f is a member of C infinity M, we should of course look at a proxy function. For that we need a chart on M. Let's say a chart u, phi. So u is some subset of M, and you have phi, which carries u over to some phi of u, a subset of Rm. Now, using this particular chart u comma phi, the proxy function is defined as the composition of the function psi star f and phi inverse. Psi star f composite phi inverse. And by definition of psi star f, this is f composite psi composite phi inverse. But note that the smoothness of the function f, which is defined on n, must follow from proxy functions which you find for f using charts on n. So some subset v will be the domain of such a chart, and the map chi will take it to Rn. Now, f composite psi composite phi inverse can be certainly written as f composite chi inverse composite chi. So these two chi inverses and chi's cancel each other out. Composite psi composite phi inverse. But notice this thing here is a proxy function for f according to the chart v comma chi. And this here is a proxy function for the map psi between the manifolds m and n. And of course, for this you need charts both from m and n. You need both phi and chi. But remember, the way in which we define the smooth function, a member of C infinity n, is for all charts v comma chi used on n, f composite chi inverse will be a C infinity function. And similarly, the smoothness of the map psi between m and n, as we defined a while ago, depended on the fact that chi composite psi composite phi inverse for all charts v comma chi on n and u comma phi on m must be a smooth function. So this result is a composition of two C infinity functions on the subsets of real number tuples, and therefore, being a composition of two smooth functions, the resulting thing is a smooth function. So this completes our proof that the pullback function is really a member of C infinity m. Now, as I have stressed a while ago, a very important structure on any manifold is the collection of all its smooth real valued functions. So for n, C infinity n is very important, and it's important primarily because in addition to being just a collection of important elements, it has a ring structure. And what is very important here about the pullback is that it plays nicely with the ring structure. In other words, if you add two elements of this ring, that is, form the function f plus g and pull it back, psi star acting on f plus g p is by definition f plus g acting on psi p. But f plus g acting on psi p is again by definition f of psi p plus g of psi p. And each individual term here is really the result of a pullback function. Psi star f acting on p added to psi star g acting on p. So falling back on the definition of addition of functions once again, we see that this result is psi star f plus psi star g, this sum function, acting on the point p. And this works for all points p on the manifold M. Because this works for all points p, of course, this result is actually result about the functions themselves. So, what we have is if you pull back f plus g, the result is a pullback of f added to the pullback of g. And very, very similarly, the other important ring operation is also one the pullback behaves nicely with. Psi star acting on the product fg at p is fg at psi of p, once again from definition. And again by definition of product, it becomes f of psi of p times g of psi of p. But f of psi of p is psi star f acting at p, and g of psi of p is psi star g acting on p. And once again, according to the definition of product of the functions, but used in the other way, what we have is that the product function psi star f psi star g acting on p will give you the same thing. And once again, this works for all points p of the manifold M, and therefore is a result about the functions themselves. So psi star acting on fg is psi star f times psi star g. In other words, carry out the ring operations first, you add two functions first or multiply them first and then pull them back to M. The result will be the same as if you had pulled back the individual functions first and then either added or multiplied them. This result is going to be quite useful in establishing a lot of non-trivial things in the future. So although this looks very, very simple and obvious, it is a very interesting and important result to bear in mind. It will turn out that the pullback operation will play a very, very important role in our next topic, which is the introduction of the notion of vectors on a manifold. As we will see, there are three distinct ways in which vectors are talked about. Once we go beyond the high school definition of something with a magnitude and direction. The three ideas, which are equivalent but very different in nature, can be called the geometer's version, the algebraic version, and the physicist's version, respectively. In a geometer's version, we actually define a vector as an equivalence class between the set of all curves. The algebraic version looks and sounds very different, but actually is very, very similar. It's a linear functional at a given point. That is, something which eats up functions and returns numbers in a linear fashion. The physicist's version, looks again very different. It talks about a bunch of numbers, say n numbers in an n-dimensional manifold, that transform in a particular manner when you change coordinates. Now, exactly how all these different notions come about and why they actually mean the same thing is a rather long discussion, and that is what we are going to go into in the next lecture. And there you will see the pullback operation play a central role. But for that, we will have to wait for the next lecture. Bye for now.